The second talk of the session is AutoDiver, Automatic Verification of Differential Cryptanalysis. This is a joint work between Marcel Nageler, Shivam Ghosh, Marlene Jutler, and Maria Eschester. And Marcel will be giving the talk.
Okay, thank you for the introduction. Today I'm going to talk about AutoDiver, which is a tool to find similar things we saw with quasi-differential trails, but from a different perspective. So I think you all know differential characteristics. Usually we try to predict some output difference based on an input difference, with the intermediate differences also specified. Of course, in an attack, we usually don't care about the intermediate differences, but for simplicity for our tool, we will be focused. And of course, with differential characteristics, we saw already in the previous talks, it comes with a bunch of assumptions, and I will list some of them here. So the simple question you could ask is this characteristic even possible? Some question that we saw the answer to in the previous talk: what is the expected differential probability of the characteristic? Does the probability depend on the key? This is related, this is the hypothesis of stochastic equivalence. And does the probability of the characteristic actually properly predict the probability of the differential attack? These dependencies and issues can arise. I came up with some small toy example. So this is a toy block cipher. The S box is the S box of present with some bit permutation that looks like present. And here you can see in the rightmost S boxes, we have some differences. And what we're going to take a look at for the tool is what kind of values are necessary for this differential transition to occur. So if we have the transition from 8 to 2, at the output, this transition has probability 2/16. So we get two values at the output of this S box. So the two output values are 0 and 2. And similarly, if we take a look at the input of the bottom right S box, the two values that the input needs to take for this transition to happen are 0 and 2. And if you pay close attention, you will see that for both of these two sets, the least significant bit is always 0. So at the output, we always get a 0. At the input of the next S box, like here, okay, this mouse is so at the input, we always need 0. So we can conclude that the key that connects these two values must also be 0, because otherwise it would be flipping a 0 to a 1. And what also happens is that if this key is 0, at the bottom right S box, the LSB, the least significant bit, will always be 0. So the probability will be 2 divided by 8 instead of 2 divided by 16. Okay, so this is a toy example, and now we want to find some way to actually detect these issues and properly address them in our research. And the simplest, but also most hardest method is to do experimental verification. Of course, this is always very nice, because then you can cover all the assumptions that your attack makes, because you actually execute the attack. In practice, of course, our attacks are too slow to actually try them out on an academic budget. Some other things that you can do is you can take the theoretical approach with quasi-differential trails, and we've seen that there are also some nice techniques to calculate the EDP with this trick from the previous talk. And there the values at the inputs and outputs are kind of described by the linear masks. What we also see in related work is the work by Perrin and Tan, where essentially the idea is to propagate constraints, where each active S box forms like a half constraint, and you try to connect two half constraints together to find a key dependency. And in this work, we approach this problem from a computational angle using SAT solvers. And our idea is to create a cipher model as a CNF, as a conjunctive normal form formula for a SAT solver, and then use this formula to recover some information about the characteristics, like for what keys is this characteristic possible, what is the expected differential probability, and things like this. So for this, we propose autodiver. You give it as an input, the cipher description as a CNF. This is already done for a long list of ciphers, so maybe you don't even need to do it yourself. And you give it a differential characteristic. And as an output, it can give you necessary linear and nonlinear conditions of the keys. We also have the nice property that for the linear conditions, we know that the linear conditions are complete. So we don't miss any linear conditions. And it can also, when you have these conditions, tell you where these come from, like which S boxes cause which condition. It can estimate the probability averaged over all keys, like similar to what we saw before, and it can estimate the number of valid keys. And here you can also see the link to the tool on GitHub. Unfortunately, there's a small bug in the slide. The link should be Isaac-TU-Graz, not TU-Graz-Isaac. But at least in the paper, it is correct. Okay, so we need the description as a CNF. How do we actually formulate this CNF? So what we want to do is we want to encode the encryption process of the block cipher as a CNF. And for that, we formulate the linear layer using the XOR formulation. We formulate the S boxes. So here we actually make sure that the plaintext, the input and output of the S box of every S box correspond to like the actual lookup table of the S box. And for the active S boxes, we need additional constraints. Because remember, we're trying to find the satisfying pair for the differential characteristic. So what we do for an active S box is that the input and output must also follow the differential transition as it is specified in the characteristic. And for that, it would be cumbersome to do it manually for each possible input-output mask. So we create it automatically with the Espresso logic minimizer. So now we have a description of the cipher that also incorporates the characteristic. Now, what can we do with it? Well, the simplest thing that we can do is we have the characteristic description, and we just let the SAT solver solve it. And with that, we can detect impossible characteristics. Because if the SAT solver says there's no solution, we know, okay, there can be no solution to these characteristics. Or alternatively, if there is a solution, the SAT solver will give us the solution. And then we also have a proof that the characteristic is possible because we get a proper message pair, plaintext pair with associated key that actually follows this characteristic. But that is only the start. So the next logical extension is to fix the key to some value and then like try it for say 1,000 keys or 10,000 keys. And with that, you can approximate the number of valid keys. Like if for 1,000 keys, it works for about 500 of them, it's reasonable to expect that this property carries on. And of course, you can then also do some statistical analysis to give some error bounds for what the expected ratio is. And one interesting thing that you can do with a SAT solver is that if you call the SAT solver the correct way, like if you specify the key that you're constraining as a set of assumptions, there's like initial decision variables for the SAT solver, then if you have a key that leads to an unsatisfiable result, then the SAT solver can give you a so-called conflict clause, which will be a clause over the keys that tells you an extra piece of information about the key that it's like a necessary condition that you need for the characteristic to work. And so this is one way where you can properly learn conditions on the key. Essentially for each unsatisfiable key, you get a clause, which is very nice. You get So like if you have, for example, long XORs, you need like exponentially many clauses to represent these long XORs. So to address these limitations, we propose a more systematic way of learning linear conditions, at least. So the idea is that we take the same SAT problem from before and solve it with a random seed k plus 1 times, where k is the number of key bits that we're looking at. And then we get k plus 1 keys for which the characteristics works. And then we can take the affine hull of all these keys. It's like the linear hull, but with an extra offset. And for this offset, we need the plus 1 key. And then based on the affine hull, we might see that this affine hull is not of full dimension, but of reduced dimension. And then we can formulate a conjecture, because in the affine hull, we can say, okay, we have some matrix times the key equals some constant as a description of the affine hull. But of course, at this point, it's only a conjecture. So to prove the conjecture, we use the SAT solver again to find a counterexample to this conjecture that we have. And if the SAT solver says this problem of finding a counterexample is unsatisfiable, we know there is no counterexample, so we have a proof that the key must be within this affine hull. And if we get a counterexample, then we can just add this key to our set of keys, calculate the affine hull again, and try again. At some point, it will stop, either because the affine hull is complete or because the affine hull is full dimension, or because there is no counterexample. This was a bit abstract, so we'll give a small example from before. So here we would solve this characteristic 49 times, and then we would gather 49 values of these 3 keys, and we would see that the affine space would be only of dimension 47, because this rightmost value would always be 0. So we would conjecture, okay, this key bit is 0, and to prove this, we tell the SAT solver, okay, solve this problem with the additional constraint that this key bit is not 0, and then the SAT solver will correctly identify, okay, this is unsatisfiable, therefore we can conclude that this key bit must be 0. I also promised that the SAT solver tells us why this key bit is 0, at least to an extent, because right now, like if you have a very long characteristic, you don't really know where this would come from. So what you can do is tell the SAT solver to find the relevant S boxes, like the 2 red marked S boxes here that lead to this contradiction. And we do a similar thing. So we add an additional variable for each S box. We call it SRI, and for round R and index I. And if this variable is 0, then essentially all the clauses for these S box are removed from the CNF. If the variable is 1, the clauses are present as normal. So this is like a normal implication relation. And then what we can do again is solve the problem where we search for the counterexample. But this time, remember the assumption variables we had earlier. This time we add the S-box variables as assumptions. And then we'll get a conflicting clause over the S-boxes. So in this case, we would get the conflict clause not as 0, 0 or not as 1, 0, indicating that we would need to violate one of the 2 S-boxes for the characteristic to work. And that way we can reliably identify which S-boxes cause this key constraint. So this is like a method for finding key dependencies. I also told you a bit that you can find the probability. This might not be clear yet how you can find the probability. And for that, we need some extra background. Namely, there's this field, it's called model counting and also approximate model counting, which is like a research area that is associated to SAT solving. They also have like for SAT solvers, there are these yearly SAT competitions. There's also yearly model counting competitions. And in this field, we use the approx.MC model counter. And essentially what this model counter does is you give it a CNF formula F, a tolerance epsilon, and a confidence parameter delta, and an optional set of variables to count over. And then it outputs the approximate solution count C with some statistical guarantees. So essentially the guarantees are that the ratio between the approximate count and the correct count is within 1 over 1 plus epsilon and 1 plus epsilon, with probability of at least 1 minus delta. And this is like, then you have some kind of proof about that the construction of the approximate solver guarantees these statistical guarantees, And actually, in our experiments, at least, we noted that this probability of 1 minus delta is like a lower bound, and in practice, the answers seems to be correct much more often, like essentially all the time, for at least our cryptographic examples. And the idea is then to count this, to use this to count the probability or the number of valid keys. And that way we can formulate again the block cipher, include the key schedule, and then we can count the number of valid pairs with associated keys for the characteristic to work, and then divide to get the probability. So with that, we can go on to some results. So we implemented this for many different kinds of ciphers. And because it's a SAT problem, it's quite versatile. You can apply it to many different kinds, like strongly aligned SPNs, weakly aligned SPNs, Feistel ciphers, and ARX ciphers. And this allowed us to confirm many key dependencies that were already discussed in the literature, for example, for Skinny or so, and also find many new ones for ciphers where this analysis was not yet done before. Overall, we see that the method from the beginning of finding the affine hull, like the systematic learning of linear conditions, works best as we increase the number of rounds, because here the SAT solver has some additional degrees of freedom, and ApproxMC is reliable but slow for many rounds. I will skip this slide. It's some example results from Midori, where we verify the characteristic at a probability of 2 to minus 52 quite quickly, but I'm already running a bit late on time. Here you can see some example usage of how it would look like if you run it in the terminal. You give it the cipher name, a file for the characteristic, and the command that you want to run, and then it prints out all the key dependencies it finds. So to conclude, we have presented a tool to verify differential characteristics. We can show whether a characteristic is possible or not, and if it's possible, we can find a satisfying pair. We can estimate the expected probability of the differential characteristic, and we can find linear and nonlinear conditions on the key. Some open questions that remain is whether the probability of the differential distinguisher is larger than that of the characteristic, and if you have a variation of the probability across different keys, you need different tools. So what we mainly find is the keys for which the probability is 0. But for example, with quasi-differential trails, you can also find some more variations if there's like a space of keys where the probability is a bit higher or lower. And yeah, this concludes my talk. Thank you all for your attention.
Thank you. Any questions?
Thank you for our talk. What is the largest size of the S-box you considered?
So the largest would be the 8-bit skinny S-box. But you can create a SAT model for other S-boxes as well, but we didn't really, we mainly focused on newer lightweight ciphers. But that was more like a design choice, not a limitation.
Okay, thank you.
So my question is, you had weakly aligned and strongly aligned, and you had pure SPN. So what's the definition of that? And what if you have like a bit permutation plus some aligned matrix? So where will it fit in this?
So the definitions, maybe we can go back to the slide. For pure SPN, I called pure SPN is the one where you have only only a bit permutation between S boxes, and yeah, the proper definition is probably like a very hard question. But really, since we're doing a SAT model, you can also create a SAT model if you have a cipher that has a bit permutation plus a mixing layer. For example, if you're thinking of something like Orthros or so, this could also be formulated.
But it will not fit, like it will have to be a new category, or will it fit in one of these?
Well, these there's not like the categories are just here to outline that you can have different things. In the code, they're all handled pretty much the same.
Okay.
Thank you for the talk. So I have a question. So when your SAT model returns SAT, does it mean you find a right pair for certain K? Characteristics. So does it mean the SAT will prefer to find some Ks with a larger probability? Because because for some K, if the probability is very, very small, then it's very hard to find a right pair.
I'm sorry, I don't really understand the question. So in what context are you asking? Like in the context of finding the key conditions or some other context?
Yes, because my first question is your model is to find some right pair under some K, but the K is actually not selected by you. It's selected by the tool, right?
It depends a bit. Like for the in this model here, the key is selected by the tool, and or I guess here. But in the previous model, you can if you want to find nonlinear conditions, I would choose a random key and then solve, and then either a right pair exists or not.
So you will first choose the K and use the K in the search.
Yeah. In this case, I choose the key randomly, and then the search is also more complicated because the SAT solver has fewer degrees of freedom. And in the other case here, the key is selected by the SAT solver. And then we might need some constraints on the key or so to see what happens.
Okay, thank you.
Other question?